Dear students, we are talking about fluids at rest in continuation only. Previous classes we have discussed about the Pascal's law. We have taken the liquid at rest in any of the container. Means we are not giving it any motion, we are not moving the liquid, we are simply keeping it at rest. Then pressure at any point, of course, we can find by the height of the liquid. And force which is acting is always perpendicular, that is known as thrust. And when we are talking about the liquids at rest, then liquid is in a container. So if I talk about the various forces of attraction between the bodies, then I can have the forces with me like the adhesive forces and the cohesive forces. Cohesive force is between the water molecules, due to which if you are putting it in some other container, you are able to move the whole water from one container to another container. And when the liquid means the water, if I have taken the water as the liquid, then it is in a glass container, supposingly if I am taking, then there are certain forces which are there between the water and the glass molecules. Those forces, they are known as adhesive forces. So if I'm having some liquid in a container, I can have two type of forces with me. One are adhesive forces between the different type of molecules. It means between water and glass or water and plastic, whatever container you are taking material. Cohesive forces, they are the forces between the water molecules or similar type of atoms or molecules. The forces which are acting, they are termed as the cohesive forces. Few more definitions along with these two definitions you have to do is, one is molecular range. Now if I'm taking any one molecule here of the water, then it is able to apply its force of attraction up to a particular distance. Like when we discussed about the gravitation, we said Earth is able to attract the things up to a particular distance. That is the range of the Earth's attractive force. Similarly, here when I am talking about the molecule, this molecule, a molecule, if I have taken inside the liquid or water here, then it is able to apply its force of attraction up to a certain distance, that is its molecular range. As if I can hold up to this my one hand distance, that is my range, I can hold the things from this much distance. If the thing is going beyond this, then I will not be able to hold up the things. So this is the molecular range. And if this molecular range taken as the radius, if I take this molecular range as a radius, then and I draw a sphere, that will be known as a sphere of influence. It means R is the molecular range and the sphere taken R as the radius, that I may call it as the sphere of influence. And what is surface film? If I take a film here on the uppermost layer, having the thickness equals to the molecular range, then that is making the surface film with you. And write it, that the thickness of the uppermost film having T equals to R. It means thickness equals to the molecular range, that is making the surface film. So these are the three definitions which we will be using very frequently. These three definitions, you keep it in your mind. And then we can move ahead with the things. Now what is, taking this liquid in the container, then because if I'm bringing the molecules to the upper surface, then you must have observed, if we ask you to put an iron needle which is heavy actually, But if you put it gently, you can put it on the upper surface. It means this is the surface film of the liquid, and if I'm putting a needle here, I'm able to put it, if I put it gently, I'm able to put the needle over the surface. Because this upper surface behaves like a stretched membrane, and this property due to which the upper surface film of the liquid, it behaves like a stretched membrane. This is actually the surface area decreases for the uppermost layer, which is your surface film, so as to get the stability. So this property by virtue of which the free surface of the liquid at rest, it behaves like a stretched elastic membrane, is termed as surface tension. And this surface tension you can denote by T or you can denote by sigma. Surface tension is denoted by either sigma, this is the sign sigma, simply you can make, or you can write it by T. This is pronounced as sigma. Or T simply for surface tension, but most of the times I use sigma. So it is your choice. You can go with T also. Now this upper surface, if you take, then the force is acting perpendicularly to this line. If I take the line length L, then force per unit length, mathematically if I write, that is giving me the surface tension. And the units for the surface tension, of course, Newton per meter. Or if I want to write the dimensional formula, that is force upon length. It means mLT minus 2 upon L. I'm getting mt minus 2. This is the dimensional formula. Now the question is that why this upper surface behaves like a stretched elastic membrane. This property is being observed experimentally, and you people have also observed. Now we are going for why it behaves like the stretched elastic membrane. For that, you are having the molecular theory of surface tension. So this is the molecular theory of surface tension. If I am taking here 3 molecules with me, I have taken, then this is the surface film, the uppermost layer of the liquid. This, which is thickness, is equals to the molecular range. If I am having the molecule A here in deep inside the water, then you can see the forces which are acting, upward forces and downward forces, they are equal. Now if I'm talking about this molecule, B molecule with me, then if I take this as the molecular range and draw a sphere, you can see more than half the sphere is lying inside the water. So here if I draw, this is the diameter, then downward forces are more, because upward liquid is up to this, then the upward force. And if here I take C molecule, then above the surface there is air. When I'm not having any water, so here it is air. This is water. So no upward force is there due to water. So only the downward forces are acting. So what it is happening actually, if supposingly I want to bring a molecule from here to the upper surface, then I have to work against these downward forces. And that work done is being stored as the potential energy. And for the stability of a liquid at rest, this potential energy should be minimum. This is the condition for getting the equilibrium or the stable equilibrium. The potential energy must be minimum. So if I want the potential energy minimum, then it means number of molecules on the upper surface should be less or the minimum. And to have the less number of molecules on the upper surface, it should be having of course minimum area, or when it is minimum area, then of course it behaves like a stretched elastic membrane. So this is why the upper surface is behaving like a stretched elastic membrane. And because it is behaving like a stretched elastic membrane, so this property we are calling it as the surface tension. And it is simply behaving to have the potential energy minimum. And the same can be the reason if it is asked as a conceptual problem that why the raindrops are spherical. Because spherical surface is having the minimum surface. So to have the minimum area, number of molecules are less, and then it is behaving like a stretched elastic membrane. This is the by nature. Everybody wants to have equilibrium. It means everyone wants to have stability, and to have stability, this surface tension is coming into the nature. So you can write certain phenomena which you observe in your day-to-day life, which can be explained on the basis of surface tension. As I've said, raindrops, they are generally spherical, again to have the minimum surface area. Similarly, small mercury drops, if you take, they are spherical, while if you take the larger one, they tends to uh, flatten because of the weight, because the weight is more of the mercury. Mercury is heavy than of course the liquid water. And this you must have observed that if I have a frame of a soap film, I have a circular frame, I dip it into the soap solution and then I take it out. Then if you put a thread on it, it by itself, it takes the spherical shape. Or you can, if you have not seen, then you can observe this, simply do this activity at your place so as to understand the things. And on the water surface, gently, you can always put it. And when you are doing the painting, you are just dipping the painting brush into the water, then you take it out, or you dip it into the paint and then you take it out. It makes the hairs of the painting brush to cling together because of, again, to get the minimum surface area, or because of the property of surface tension. So this way, from your day-to-day life, you can observe at various places where this phenomenon of surface tension can be observed. Next term with you is surface energy. I can simply write it by S or E. Again, your energy, it is so scalar quantity, and it is equals to the work done divided by increase in surface area. So if I take a rectangular frame, like with circular frame, you have played even for producing soap bubbles. Circular frame, you dip it into the soap solution and then you blow the air, then you see the colorful bubbles coming out. That is in your day-to-day life you have observed. This is metallic rectangular frame I have taken. I'm just going to dip it into the soap solution and I'm going to take it out. See to it, this length of this frame is L, and this is of course having the movable, one side is movable. So when we dip it into the soap solution, this side AB, it by itself moves to this distance x and takes the position A dash B dash. Because of some force is acting on it, and that force is equals to of course this surface tension which is acting, because when you are dipping it into the soap solution, two films are formed, and the force which is acting perpendicularly, that is surface tension sigma. And when two layers are there for the soap solution, then twice of sigma. And we have discussed the surface tension sigma, it is equals to F upon L. F upon L. And so from here you can write F, it is equals to sigma into L. And because two films are getting formed, so tension force will be here twice. So you can simply replace this force by twice of sigma into This is the force which is acting. And when I want to find the work done is force into distance. Distance I have taken x. So this is the value of the work done, 2 sigma L into x. So surface energy is what? Energy is equals to work done. And work is done for simply increasing the surface area, because this distance, if I take the breadth as b, then this is getting increased by this distance x. So this much distance is getting moved because of the force. So from this formula, if you put the value of the work done here, which is 2 sigma Lx, and how much is the increase in area? That is of course final area minus initial area, or simply I can say that increase in area is twice of this L into x. So 2Lx, that is the increase in area. And if you put the value for the surface energy, we are getting work done is 2 sigma Lx. Increase in surface area is 2Lx. So you can see this Lx is getting cancelled, 2 is also getting cancelled. So I'm left with surface energy, that is equals to sigma. So numerically I can say that surface energy is coming equals to the surface tension, but both the concepts are different and you should be able to differentiate between the surface energy and surface tension, and this I may take as the relation between the surface energy and surface tension. Surface, if I'm having a curved surface with me this way, then what about the pressure difference across the curved liquid surface? When the surface is plain, like I took water in the container, because water is an ideal liquid. So for the ideal liquid, I have said that the surface is plain surface. So the sigma, here I can say the pressure because of the air, that is vapor pressure, pressure due to the liquid, that is liquid pressure, both are equal, and that is why the surface I am getting plain. Though if water is also not your ideal liquid, and so actually if I have in general tap water is having certain impurities, so you get it like this concave surface, concave upwards. So if I'm having concave upwards, or I can have the liquid for mercury like I'm having this convex upwards. So because of the pressure difference, it is getting this shape, which is which can be said as the meniscus. So shape of the meniscus is to be decided by the pressure difference. Here, because if you see the surface tension, that is the tangential force acting perpendicularly. So if you are drawing the tangent to get sigma, of course, and then if you resolve it, if I'm taking this angle as theta, then I may say sigma cos theta, and then here also sigma cos theta, they are going to get cancelled, while sin theta components will get added. So here the pressure of the liquid is getting more than the pressure of the vapor. So this case, and as a result, to maintain this meniscus, the excess pressure will come from downside, from the liquid side, it means, to get the meniscus maintained. Again, you can mark the direction for the sigma, that is the surface tension force, which always exponentially, and then you resolve, then force, extra force, which is coming this way. So excess pressure has to come from this side just to bring the equilibrium. Again, I have said equilibrium is the stable equilibrium is the requirement for everyone. Everyone wants to be stable. So excess pressure is coming again from this side, from the vapor side here. But you see the excess pressure is always acting on the concave meniscus. So if the concave meniscus is upward, this is coming from this side. If this is concave meniscus is downward, then excess pressure is coming from this side. And that is why when you see in your day-to-day life, you see the air bubbles, when even if you play, as I said, with the circular ring, dipping it into the soap solution, then you make the bubbles. those bubbles also split after some time, because when you are taking this drop or the bubble, then excess pressure is acting outward, and due to which it will increase its area, and that increase in area will further result into the bursting of the bubble. So this is again, you can see it is coming from the concave side. So excess pressure always acts from the concave side. Pressure inside a liquid drop, if I take a liquid drop or I take an air bubble, the value will be the same. If I'm saying that earlier the radius of the drop is r, and because of the excess pressure the radius is getting increased by the value dr. Small p I'm taking as the excess pressure, which is always acting in the outward direction. dr is the increase in radius. Then initial surface area is of course 4 pi r square, and the final surface area you can find 4 pi into r plus dr whole square. And you can work it out, r square plus 2r dr plus dr square. This dr square, because dr is very small quantity, so square of this small quantity can be neglected. So I can write the increase or the final surface area with me is 4 pi r square plus 8 pi r dr. This is the value for the final surface area. And if you want to find the increase in surface area, then final minus initial. So this 4 pi r square will get cancelled, and I'm left with 8 pi r dr. And from the definition of the surface energy, we have done work done, which is there in enlarging the drop, that is equals to the increase in the surface energy, which is equals to the increase in surface area into surface tension. If surface tension I assume sigma, then work done I can find that is coming out to be 8 pi r dr into sigma. So, but from the other definition, then work done, that is equals to force into distance, and force is pressure into area, and pressure, excess pressure, I have supposed P, small p, that is the excess pressure with me, and area is 4 pi, earlier radius is r, so 4 pi r square, and distance it is moving is dr. So these both are the values for the work done, one from the definition of the surface energy, another from the normal definition of the work done. Equate both these values. On equating the work done of both these equations, first if I equate, this pi 1 r dr will get cancelled, and I'm getting excess pressure is 2 sigma upon r. Sigma is of course the surface tension, r is the radius of that liquid drop or of air bubble. So for air bubble also, all these same steps has to be done, and you will be able to get the excess pressure inside the soap bubble. But if I'm having a soap bubble, then soap bubble has two layers. So soap bubble has two layers, so increase in area will be twice. So when I write the effective increase in area, rest of the things you have to write the same. But if I want to put these values for the increase in surface area, that is equals to 2 into 8 pi r dr. It means increase in surface area is of course 16 pi r dr. This is the value for the increase in surface area, and so work done will be equals to increase in area into surface tension, but it is can be written as force into distance also. So again I'm getting these two equations with me for the work done, and when you equate these values of the work done, I'm getting the excess pressure here, that is equals to 4 sigma upon r. So excess pressure, this is of course which is always acting on the concave side of the meniscus. So this way you should be able to derive the expression for the excess pressure, whether they are asking for air bubble, liquid drop, or for soap bubble. So keep things up to this for today. Thank you everyone.